Okay, so this is section 10.4, which is lines and planes in space. So you can read our objectives. We're going to find parametric and symmetric equations for lines in space. We're going to find equations, sketch planes, and find distances between points and planes in space. So first of all, we're going to look at lines. So when you think back to when you learned how to write equations of lines, we used slope when it was in a plane. But now we're in 3 dimensions, we're in space. So we use vectors that are in the same direction as the line that we're trying to find the equation of. So we're going to use vector v, which is parallel to the line that is formed between points P and Q. So vector v, we're calling a direction vector. And the components of vector v, which are a, b, and c, are our direction numbers. So if we think about this, PQ is the vector that we're trying, or the line that we're trying to find the equation of. So PQ is formed by taking x minus x1, y minus y1, and z minus z1. Those are our 2 points P and Q. So vector PQ is going to be a scalar multiple of v. So v was a, b, and c. So we can take a scalar like t and multiply it by a, b, and c. So at, bt, and ct would also represent, or t times vector v. So to get the parametric equations of the line, we're going to use all of this. So if you think back to what we had here, so we're taking that these are equivalent. So x minus x1 would equal at, y minus y1 would equal bt, and z minus z1 would equal ct. So we're going to rearrange those equations so that it's x equals, y equals, and z equals. So that's where we get x equals x1 plus at, y equals y1 plus bt, and z equals z plus ct. So these are our parametric equations, and then from that we can get the symmetric equations. So if you see, each of these has a t in it. So if we were to solve for t, which would be the same value for all of them, that t would equal x minus x1 over a, or y minus y1 over b, or z minus z1 over c. So those are our symmetric equations. So example 1, we're going to, in the parametric and symmetric equations for line L that passes through the point 1, negative 2, 4, and is parallel to vector v. So the first thing that we're going to do is find the set of parametric equations. So we know that our x1 is 1, our y1 is negative 2, and our z1 is 4. And then our direction numbers are 2, 4, negative 4. So here's a picture illustrating that. So we have our x1, y1, z1, and our a, b, c. So we can fill those in to, if we go back to the previous slide, so this is our x1 and our a, there's our y1 and our b, and our z1 and our c. So then if we solve each of these for t, you can rearrange this in your mind here. It'd be x minus 1 divided by 2, and then y plus 2 divided by 4, and z minus 4 divided by negative 4. So that's our symmetric equation. Okay, so planes in space. So we just saw how the equation of a line in space can be obtained from a point in the line and a vector parallel to it. So what we're going to do for a plane in space is we are going to find a vector that's called the normal vector. And a normal vector is just a vector that is perpendicular to the plane. So if you look at our picture over here, we have the point x1, point P, which is x1, y1, z1, and has a non-zero normal vector. So this n right here is our normal vector that's perpendicular to the plane. So the plane consists of all the points Q, which x, y, z, for which the vector PQ is orthogonal to n. So we can use the dot product. So we can take n and take the dot product of n and vector PQ. And remember, orthogonal means 90-degree angle. So this right here is our directional numbers, okay? And this is the distance between the points. So we have x minus x1, y minus y1, z minus z1. So if we take the dot product between these, we have a times x minus x1 plus b times y minus y1 plus c times z minus z1. So this third equation right here is the equation of the plane in standard form. So, and then we can see in the box here, that's the same equation that we saw on the previous slide. So if you regroup the terms into the general form of the equation of the plane, so just ax plus by plus cz plus d is giving you your general form of the equation of a plane. Okay, so we're going to find the general form of the equation of the plane passing through the points, passing through these 3 points. Okay, so in order to do this, we need a point in the plane and a vector that's normal to the plane. So we have 3 points. So we have a point in the plane, but we don't have a normal vector. So we need to find a normal vector. And if you think back to the previous lesson, 10.3, finding something that's orthogonal to two vectors would be the cross product between them. So if we have right here, so this is a picture, so what we want to do is we want to find the normal vector, and we're going to use the cross products of vectors u and v. So we're going to use the point 2, 1, 1 as our starting point. So we're going to find this as u, and this would be v. So to find that, we're going to take, so for vector u, we're going to take 0 minus 2, 4 minus 1, 1 minus 1. So that would give us negative 2, 3, 0. And then to find v, we're going to take negative 2 minus 2, which is negative 4, 1 minus 1, which is 0, and 4 minus 1, which is 3. So that's what we're doing right here. So we get negative 2, 3, 0 for u, and we get negative 4, 0, 3 for v. So we're going to take u cross v, which is what we did in section 10.3. So you can go back and look at that if you're not sure. But we're going to find, so you'd find those determinants of those smaller 2 by 2 matrices. So we end up with 9i plus 6j plus 12k. So these are our A, B, and C values that we're going to plug into that equation. So this is the normal vector to the given plane. Okay, so now we have direction numbers for n, and then we have the initial point, which we chose was 2, 1, 1. So there's our 9, 6, 12, our A, B, and C, and then we're plugging in 2, 1, 1 for our x1, y1, and z1. So if we simplify this all out, we get 9x plus 6y plus 12z minus 36 equals 0. And then we can, since it's divisible by, since all the coefficients are divisible by 3, we can do that and simplify it into 3x plus 2y plus 4z minus 12 equals 0. And so we can check that all 3 of the points satisfy the equation. So you can plug in your x, y, and z from the 3 points that are given to make sure that they make the equation true. Okay, so 2 distinct planes in 3-vector space are parallel, or they can intersect in a line. So this is a picture here where we have the pink plane and the blue plane, and they're intersecting at this line right here. When they intersect, we can determine the angle of intersection by using their normal vectors. So the angle between the normal vectors, you can see n2 is for the pink plane and n1 is for the blue plane. So the angle between those 2 normal vectors is going to tell us the same angle between the 2 planes. So we find that using, so the cosine of the angle is going to be the absolute value of the dot product of the 2 normal curves, or the 2 normal vectors, and divided by multiplied the magnitude of each normal vector. So knowing that, if we take the dot product and it equals 0, that means that they're perpendicular, and they're going to be parallel when one of the normal vectors is a scalar multiple of the other. Okay, so sketching lines in the plane. So to sketch, we're going to find the points of intersection with the coordinate axis. So if we have this equation right here, so 3x plus 2y plus 4z equals 12, you're going to find all of the traces, if you remember back to section 10.1. So we're going to do that by substituting 0 in for each of our variables. So if we put 0 in for z, we end up with this equation right here. So then if you do the cover-up method where you cover up y, that would mean x has to be 4. So that's where we get 4, 0, 0. And then if we cover up the x value, 2y equals 12, so y would have to be 6. So that means that the xy trace is going to intersect the x-axis at 4, 0, 0 and the y-axis at 0, 6, 0. So you can see that right here. Then we would do the same thing to find the yz trace and the xz trace. So you can see that by finding all of those intersection points, it makes a triangular plane that we have here. If the equation of a plane has a missing variable, so like this one's missing a y, it means that the plane must be parallel to the axis represented by the missing variable. So you can see that this plane would be parallel to the y-axis because it's missing the y value. If it's missing 2 variables, then it's going to be parallel to the coordinate plane that's represented by the missing variable. So if we have, so like this has an x in it, but no y or no z, it's parallel to the yz plane. If it has a y, it's parallel to the xz plane. And if it has a z, it's parallel to the xy plane. Okay, so distance between a point and a plane. So the distance between a point Q, so here's our point Q, and the plane is the length of the shortest line segment that connects them. So we're going to use this idea of a projection, projecting the vector PQ onto the normal vector. And so what this is going to simplify to is we're going to take the absolute value of the dot product between our vector and the normal vector divided by the magnitude of the normal vector. So to find a point on the plane, given by ax plus by plus cz plus d equals 0, so where a can't be 0, we're going to let y equal 0 and z equal 0. So here's our point Q, and the plane 3x minus y plus 2z equals 6. So our normal vector, we're taking the 3, the negative 1, and the 2, so there's our normal vector to the given plane to find, and our point Q right here. So we're going to let y equal 0 and z equal 0 in our equation and obtain, so if we do that, if we let these equal 0, we have 3x equals 6. So that means x has to equal 2 when y and z are 0. So point P is going to help us find the vector from P to Q. So we're going to take vector PQ, we're going to take 1 minus 2, 5 minus 0, and negative 4 minus 0. That's where we get negative 1, 5, negative 4. Okay, so to find the distance between our point and the plane, we're going to take the dot product of that vector we just found and the normal vector and divide it by the magnitude of the normal vector. So here's our vector PQ that we just found, and we're going to do the dot product with our normal vector, which was 3, negative 1, 2. And then this is coming from, so 3 squared is 9, negative 1 squared is 1, and 2 squared is 4. So that's the magnitude of our normal vector. So remember, dot product is -1 times 3 plus 5 times -1 plus -4 times 2. So that's where these numbers are coming from. It's going to be the absolute value. So we're going to get 16 divided by the square root of 14. So this right here would be the distance between point Q and our plane given by that equation. So that's it for section 10.4. Let me know if there's any questions or anything I can provide more clarification on. Thanks.